Today we will be talking about lipids. Okay, so we're going to be talking about lipids, which are just fats. Okay, so what exactly is a lipid? What are fats? Well, fats are essentially little storage cubicles for energy, right? So imagine like a crate filled with energy. That little block, that little crate is a lipid, okay? And you're going to be finding lipids in the natural world in the form of fats and oils. So they can be fats and oils. Now, typically you normally get fats from animals and oils from plants. That's kind of like the general observation. So you can get it from animals. And oils come from plants. Okay, there are exceptions, of course. So, for instance, fats would be lard or tallow. McDonald's back in the 80s used to use tallow for their fries. So tallows would be rendered beef fat. It's very unhealthy. Fats typically are saturated fats, okay, which are not good in excess. But oils, you'll find them like canola oil, olive oil, etc. Okay, and oils tend to be unsaturated, and unsaturated are very good for your body. So you typically want to have more unsaturated fats in your body. So you can say can be saturated. Let's just put sat for saturated, and we can put unsat. That is unsat, UNSAT, for oils. Okay. So what exactly is saturated and what is unsaturated? Well, all that means is that, well, lipids in their basic form are just carbons connected with other carbons, and they have a bunch of hydrogens, okay? So let's draw an unsaturated, let's draw a saturated fat first. So we have a carbon, and another carbon, another carbon, another carbon, and it could keep going for a long amount. Typically they're 18, typically, right? And of course you have your hydrogens here, right? So you can see that this is going to be a little gruesome because I have to draw out these hydrogens, but that's fine. So notice that this carbon has a bunch of hydrogens, right? This is kind of like a basic form. I'm not drawing a complete lipid, okay? It's very simplified. But this carbon is saturated. Now, the reason why we say it's saturated is because all the carbons have all of its electrons occupied. What does that mean? I'm just saying that carbon can no longer connect to anything else because it has its maximum connectivity. All the carbons are occupied with hydrogens. So saturated, sat, means all carbons have hydrogens. That was pretty bad. So we can say have hydrogens. Okay. Now, what about unsaturated fats? Well, since we did 4 carbons, we're going to do another 4 carbons right here. But over here, you're going to notice something different. And you notice that I inserted a double bond. So you can see that unsaturated fats always have at least one double bond. Let's say 1, 2, 3, 4, there we go. And then we're just going to do this, okay? Always make sure your carbons have 4 bonds, okay, not 5. That you'll get in some trouble with that. So we have some hydrogens right here, and notice again that we have a double bond, so that's always fun. Okay, we're going to be talking about unsaturated and saturated fats later on. I just want you to understand the difference between them. Okay, so right here, notice that not all my carbons have the maximum amount of hydrogens possible. Okay, because of this double bond, we're going to have some carbons that don't have the maximum amount of hydrogens. See, the max that this carbon could have had is 2, but now this carbon only has 1 hydrogen. And this carbon, instead of having 3 hydrogens, only has 2 hydrogens. Weird. And it's because of this double bond. Okay, so that allows imagine that you have a cluster of lipids. That makes the lipid more fluid, more flexible, right? And why is that? Well, over here, you're going to have, we're going to get into it more in this video, but let's say you have your polar group. So this is going to be a polar head. And then we're going to have our fatty acids. So you can just imagine that as a fat. Let's say that this is saturated. Okay? And then we're going to have a cluster of this. Okay, so notice that because the fats, the lipids, the tails, are straight, they can be compacted very, very tightly. Okay, so I repeat, saturated fats, when you join them together, can be packed very, very tightly. But what about unsaturated fats? Well, unsaturated fats are a bit weird. You're still going to have your polar heads. That doesn't change. But instead of having this nice zigzaggy tail, you're going to have this. Okay? And that's kind of weird. So if I try to put them together, sometimes it'll collide. And you don't want that. So instead, what you see in nature is that you have this guy right here, and then you're going to have another guy far away from it, because these guys take up more space, right? So over here, you can have something like this. Okay? So typically, unsaturated fats have a large kink. We can call them kinks. And that's essentially where the double bond is, okay? And that double bond takes up a lot of space and makes it so that you cannot compact a lot of them together. Now, since they're further away, they can wiggle around, they can move, and that makes it more fluid. That's why oils, which have more unsaturated fats, move around, okay? Whenever you put olive oil on a pan, you can move it around the pan. You can't really do that with a stick of butter, can you? So if the pan has no heat on it, the butter doesn't really move. However, oil always moves, okay? And that's because of unsaturated fats, unsaturated oils versus saturated fats. So now notice that we have this saturated fatty acids. You could just think of lipids, okay? So because they don't have any double bonds, they can be put together really tightly, and that makes it more rigid, more structured. But over here, you can have a combination. You can have a combination of saturated fats and some unsaturated fats. So notice that these unsaturated fats cannot really be placed close together because they take up a lot of space, and that allows a more flexible structure. Okay. So in this class, we're going to be focusing on 4 different type of lipids. Okay, so the 4th one that I'm going to be talking about is not shown on this picture, and I'll just explain it to you. But for the ones that are shown, we have the triglycerols. Okay, so this is actually triacylglycerol, but you can also call it just triglycerol. Okay, so you can have triglycerols. Of course, I can never spell, so we have triglycerols, and this is going to be phosphoracylglycerol. Of course, you can call it glycerol phospholipids. It's just random, however you want to call it. It's all preference. For preference, I'm going to be calling triacylglycerols triglycerols, okay? And we also have some sphingolipids. So what is the difference? Well, the difference is that for triglycerols, they're going to be nonpolar, okay? So they're going to be nonpolar. And that's because of a lot of fatty acids. Now, fatty acids, again, are just carbons with hydrogens. That's not going to be very polar. It's actually not polar at all. So because triglycerol is made from nonpolar substances, triglycerol itself is nonpolar. Now, what about glycerol phospholipids? Excuse me. Well, glycerol phospholipids are polar. Now, you may be thinking, hey, I've heard of those, and you should. Your membrane in your cells are actually made from phospholipids. We can call that phospholipids. And what makes this polar is actually the phosphate group, okay? The phosphate group has an alcohol, and that's going to make it polar. So whenever I drew this right here, this was your polar head. Well, this guy is your polar head, and your fatty acids are actually the tails, okay? So we have fatty acids. So I think that's pretty cool, right? And then we got the sphingolipids. Sphingolipids are actually polar as well. So polar, we have polar, okay? And that's kind of all you need to know right now, okay? And we also have a fourth type. And we're going to call that non-saponifiable lipids. Okay, so what's a non-saponifiable lipid? It's essentially, it's like almost similar to these guys, except instead of fatty acids, you can have rings, okay? So what do I mean? Imagine a cholesterol structure. A cholesterol structure just has a bunch of cyclohexanes connected to each other, and they're going to be connected to a glycerol, okay? So that's what a non-saponifiable lipid is. It's just a lipid with a bunch of rings in it. Why does that matter? Well, you can actually use non-saponifiable lipids to make steroids, okay? So those are always interesting, right? That's all I'm going to say. So you can make steroids, okay, and hormones. And finally, cholesterol. Now, here's a fun fact. Cholesterol is actually the building block for a lot of steroids and hormones. So whenever scientists are trying to make testosterone, they first want to go to a pathway that gives them cholesterol. And after cholesterol, they could go to a neutral hormone. And from that neutral hormone, they can make testosterone or estrogen. So you can see why non-saponifiable lipids are pretty important to our scientific needs. So what is a fatty acid? So fatty acids, we're going to call them Fa. Okay, so fatty acids, you're going to call it Fa. Well, what they are essentially carboxylic acids with a ton of carbon-carbon hydrogens, okay? So essentially, they are this structure. You have this. You have HO, then right here. So here's your carboxylic acid. And then we go 1, 2, 3, 4, 5, 6, 7, 8, and then etc. Right, so it just keeps going and going and going. If you want it to be unsaturated, well, you just keep making carbon-carbons, right? So typically, FAs are typically 12 to 20 carbon-carbons, okay? So you can go like 1, 2, 3, 4, 5. Like the minimum is 12 and the maximum usually is 20, okay? And usually, there's always exceptions, they are even numbers. So usually even, and let's just put a hashtag or like a pound sign if you're from the 80s, even numbers, okay? So that's numbers, right? So how do you name fatty acids? I'm going to teach you how to name them so you can impress your friends, okay? How do they work? Whenever you want to name a fatty acid, you name it like this. You have the number of carbons, and then the number of double bonds, and finally, you also have the position, of the double bond, the position. And we're going to have a little baby triangle right there, okay? That's just, it's weird, it's random, but that's how you name them. You always have to have your little baby triangle on it, okay? So we have baby triangle, and then we're going to have the position of the double bond. So I'm just using letters as markers, okay? And I'll give you a real example. So if you wanted to draw out the fatty acid, well, what does this mean for us? What does that mean? Well, this means that overall, there are 18 carbons, and there is one double bond. Now, that double bond occurs on the 9th carbon. Okay, let's have some fun, and let's draw it out, okay? So we have our carboxylic acid, as usual. Now, this right here is a carbon, remember? So you have one carbon right here, if it makes it feel better. There you go. So that's the first carbon. So now we go 1, 2, 3, 4, 5, 6, 7, 8, okay, 9. Now we have 9. That's 9. But we know that our double bond is going to have to occur there, okay? Now, usually, unless told otherwise, assume that it is a cis conformation, meaning that the hydrogens are going to be on the same side. Usually assume cis conformation. You don't really want to work with trans, so whenever you're eating something, like maybe some Cheetos, I love Cheetos, okay? If you look in the back where the calories are, you're going to see that there are 0 grams of trans fats. And that's because trans fats don't occur naturally in nature, okay? They don't occur in nature. So in chemistry, you're not going to be working with trans fats unless you're physically making them, okay? But in nature, trans fats do not exist, only cis, quote-unquote cis fats, okay? So always assume that you're working with cis conformations. So this is going to be carbon 9. And since we're working with cis conformations, we're going to do this. So that's 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And then we're going to have our double bond right there, okay? So overall, 18 carbons, one double bond. We'll just put DB for double bond, and that occurs on the 9th carbon, okay? It is not on the 10th carbon, no. It is on the smallest number, so it is on the 9th carbon. If I had 20, dot dot 3 triangle 9, 12, and I don't know, 15, then you would have a different structure. Now, typically, you're going to have a lot of, you're going to have a table with specific fatty acids, and sometimes professor asks you to memorize like 1 or 2 fatty acids. So we're going to talk about some fatty acids, 2 of which you should know, because most biochemistry students know this. Okay, so we're going to get into it. The first fatty acid that you must know is palmitic acid. Palmitic acid. Okay. And what is the number for it? The number for this one is 16 dot dot 0. Oh, pretty simple, so it's just 16 carbons. Alright. So the reason why this is so important is because 26, and I repeat, 26% of the human fat is made from palmitic acid, right? How do I remember that? Well, here's a cool mnemonic. All you have to do is just put FATT, okay? That's all you need to know. Palmitic acid fat. Why? Well, let's count the letters. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Well, if you don't like fat, you can just put fats. So altogether, that is 16 letters. That is 16 letters. Okay? So that's how you remember it. And if you want to draw it out, you just put HO right there. And then we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So what kind of fat is that? It's a saturated fat. Okay, so this is a saturated fat, right? There are no double bonds. It does not occur. It is a 16 right there. Okay. But what about the oleic acid? Oleic acid right here. So let's draw that out. Oleic acid. Well, the reason why oleic acid is so important is because it constitutes 45% of human fat. Okay, so most of the time, whenever you're trying to burn fat, you're trying to burn oleic acid, right? So how do we find out the numbers? Well, the numbers are going to be 18, 1, okay, triangle, 9. So yeah, I kind of wrote it out for you previously, but that's oleic acid. And of course, if we want to draw it out, we do this. This already has a carbon right here. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18 right there. So that's one double bond. It occurs between carbon 9 and carbon 10. Okay, you always want to pick the smallest number. So 9 is smaller than 10, of course. And how do we remember that? Well, let's see. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. We have 9 letters on this. So let's write that out. We have 9 letters. How many words do we have? We have 2 words. Okay, so 9 times 2 is going to give us 18. There are also 9 letters right here, right? So we have this guy right here, 9 letters. And that's essentially it, right? So that's how you remember it. So you have 9 letters. 9 times 2 words is going to give us 18. And you have 1 bond. And, well, the position is going to be the same amount of letters, which is 9. So you're expecting a fatty acid that is unsaturated and is going to have a double bond between carbons 9 and 10. Okay? So hopefully that helps you remember the 2 main fats in our bodies. Now we will be talking more about triglycerols. Okay, so what are triglycerols used for? Well, triglycerols are used for storage. Okay, so they are the little boxes of energy. Triglycerols store energy in the form of fats. Okay, and what is a triglycerol made of? Well, a triglycerol is made from a glycerol with 3 fatty acids. Now, since there are 3 fatty acids, that is also known as tri. Okay, so we have tri, we have a glycerol, so we have triglycerols. Scientists are very creative with names, okay? So that's a triglycerol. All right, but what is a glycerol? A glycerol is essentially 3 carbons with some alcohols on them, okay? So it's a triol, if you want to think about it, tri-alcohols. Now, each alcohol can actually ester link with the fatty acids. So each alcohol can ester link with fatty acids. So if you remember what an ester was, it's essentially this guy. Okay, so we have a carbon, we have this guy. So notice that we have a double bond to the oxygen. We're going to have another oxygen. And then we have our continued chain, whatever. The R groups are just random carbons. It could be anything, okay? All you know is that this right here is an ester. Okay? So where do you see that on this molecule? Well, you see it over here. So we're going to call that an ester. Okay? And this right here is just going to be your R groups. Who cares? So this carbon ester linked with this alcohol. It was previously an alcohol, now it's just an oxygen. So you can have that, right? You can have that. Normally, whenever we're going to go further in the lecture, I'm going to call this position 1. So this is the position 1 right here. And this one is going to be position 2. Okay? That's going to be, it's going to make a difference when we're talking about the different lipids. This right here is just neutral because that could be position 1, right? It's the same thing as the first one. So we're just going to ignore that, okay? So it doesn't apply here. I'm just making it obvious, okay? So that is a triglycerol, right? So I think those are pretty cool. Now notice that right here, there are no polar molecules. So this is non-polar, okay? Non-polar. Your cell membranes are not made of triglycerols. They are made of phospholipids, which are polar. Triglycerols are non-polar. Okay, so let's continue. We will now be talking about a specific fat. Okay, so this is a specific fat. It's called Olestra. Okay, so that's what I mean by specific. It just means like a certain type of fat. So this is Olestra. And the weird thing about Olestra is that it's completely man-made. This does not occur in nature, okay? Now, why would scientists want to make Olestra, which is a fat that you need to know for this class? Well, the reason why scientists made Olestra is because it tastes like a fat, it registers in the body as a fat, but it is not processed the same way as a fat. Now, whenever you eat fats, let's say you are hungry and you go to the fridge and you eat 3 sticks of butter. Well, your fat is going to go into your stomach and become processed, you know, through different reactions, and some of that fat will be stored, some of it will be used for energy, etc. But let's say that you had 3 sticks of Olestra butter. Let's just imagine a product like that, okay? So it's 100% pure Olestra and you eat it. What happens? The Olestra goes down your esophagus, into your stomach, and it starts breaking down. But instead of your body storing it, it actually just passes it along. Okay, so you have the flavor and you have the taste of fat, but your body does not process it. It takes nothing from it. Now you might be saying, hey, that's pretty good, I'm not gonna get fat. Well, yeah, but the reason why this is so bad is because when Olestra is in your intestines, it's going to be taking up your vitamins. It's going to absorb your potassium, your calcium, all your vitamins in your body, and then it's going to irritate your intestines. So now you're going to have inflamed intestines and you're going to be vomiting a lot. It's not good. I remember it was very, very early 2000s where Doritos actually had Olestra in them. Okay, so certain types of Doritos were like, oh, 0% or 0 grams of fat. And people are like, oh my gosh, this is amazing. How do they do it? They didn't know that it had Olestra. It was relatively new. And whenever they would eat too many Doritos, they would have intestinal issues. So that was bad. Okay, so this is not good. Not good. Inflames tissues. Okay, so if you see anything with Olestra in it, don't eat it. So now scientists claim to have modified it and to have improved it since the last decade, but I still wouldn't trust it enough to eat it, okay? And neither should you. So inflames tissues and absorbs your vitamins. Okay, so that's just kind of the tidbit that you need to know about Olestra. And it's completely man-made. Man-made fat. So it's fake. Now we're going to be talking about trans fats. So these are trans fats. And remember what I told you is that trans fats are actually man-made. Okay, so kind of like Olestra where trans fats don't exist in nature. But how do you make one? Okay, well, before we talk about that, the reason why trans fats even came into existence is because scientists wanted to find a solid butter substitute. So they wanted something that was firm but can be easily spread, okay, on like a piece of toast. And they wanted that substitute to have what? To have a lot of unsaturated fats. Okay, so what they did was they took some liquid corn oil. Okay, so they took some liquid corn oil and they pumped some hydrogens into the unsaturated fats, okay? So you have a oily substance, you're going to shoot hydrogens at it at a very, very high pressure, and that oily substance is going to slightly become more solid. A little bit more solid, not too much, but you can spread it on toast and it still has some oiliness to it. So it's very favorable. Oh my gosh, people were going crazy about this trans fats, right? They were eating it, they were frying food in it. Some carnival people still use it to make apple fritters or something. But the issue with it is that when you do this, sometimes you make a trans fat, which is weird, right? Sometimes whenever you hydrogenate just means to add hydrogen, so this is hydrogenate. Whenever you hydrogenate some cis bonds, sometimes you get a trans bond. So the scientist's ultimate goal was to remove some cis bonds, okay? They weren't trying to make trans fats at first. But a byproduct is that sometimes you get a trans conformation whenever you shoot hydrogens at a cis bond. And that trans fat right here, this is trans fat, is bad for you. Why is that bad for you? Well, since they don't occur naturally in nature, your body doesn't have any enzymes to break it down. So your body has enzymes to break down cis bonds and monosaturated fats, disaturated fats, polysaturated fats. This one right here is a polysaturated fat because it has more than one cis bond, okay? And your body has enzymes that are able to break down that bond. But your body does not know how to handle trans fats because they've never seen it before. And so what happens is that trans fat just lingers in your body. It kind of lingers. It takes a long time to break down. And what trans fats do is that they actually raise LDL and they lower HDL, okay? So what is LDL and HDL? Well, this is bad cholesterol. Bad. Let's just do that again. So this is bad cholesterol. And this is good cholesterol. Okay? Now, if you have too many bad cholesterol in your body, then your cell membranes are going to stiffen up. They're going to become rigid, and not as much blood can pass through, okay? So if you take someone who died of a heart attack that was due to a lot of cholesterol, if you cut that heart in half, you're going to see a lot of fatty deposits, okay? So you're going to have a lot of yellow stuff in that heart, and that is because that is the presence of too much bad cholesterol, which may have been due to a lot of trans fats in that diet. Now, luckily for you and me, trans fats are banned, and they were expected to go out of our food by January of 2020. Okay, so as of now, you shouldn't have any products with trans fats. That should be illegal. Okay, so again, trans fats are the byproduct of hydrogenation. Scientists wanted to remove some cis bonds by inserting hydrogens at a great pressure. But as a byproduct, this was not intended, it was an accident. Sometimes the cis bonds get twisted into the trans conformation, and your body can't break that down. So it just sits in your body and does a lot of bad things, okay? So that is the end of part 1 for lipids. And in the next video, we're going to be talking about phospholipids. And hopefully this video helped you understand why you shouldn't eat Olestra and why trans fats are really, really bad, okay? So I hope you have a great day and that you do well on your exams.